morning. Today we'll talk about the last topic in the section on interactions, which is surface plasmon resonance, and Aaron and I are going to share the lecture today. I do have a few announcements. Of course, you know the problem set 2 is due on Monday. I'm going to be out of town on Monday, so I've decided to cancel Monday's lecture, and then we're going to revise the lecture schedule later. I'll post a revised syllabus later this week, and there may be an optional extra session, I'm not sure, but things will just kind of get shifted ahead of it. There is a possibility that the midterm exam will be one lecture later than planned, but I'm not sure. I'll let you know. So the homework is still due Monday at 10:40 a.m. And for this, we're going to have a box outside of my office, 2278 G.G. Brown, along the main G.G. Brown hallway, the hallway that overlooks the parking lot north of the building. You know, for example, it'd be great if you use the lecture time to work on the video assignment to get together in your groups. And also, as I said last time, I'd like you to sign up for your video topic no later than Monday, and then get your thoughts started. And also, take time to talk with Mustafa or me if you have questions about the scope of the topic, the papers we've chosen, other ideas you have. Really, if you think that the topic should go in a different direction than suggested by the papers, feel free to suggest that, but just kind of talk to us about it first. I think you'll do more thinking specifically about how the topic will be presented when you start meeting as groups than we did in creating the topics. Although I think we chose a set of topics that are useful and important concepts, you'll immediately have probably deeper thoughts about how to put it together than we did so far. So feel free to ask if you have questions or suggestions. Also, next week I will be posting the description of the course project. And then the process is going to be that I'll ask each of you to individually write a project proposal, kind of a 1 to 2 page thing to describe an idea you have, and the scope of that will be defined. And then after that'll be that's part of the project, a small part of the project. And then after that, you'll work in teams for the project. And so, with these things in mind, I think next month is going to be a busy month in terms of assignments, because after the spring break, we'll have one more problem set before the exam. The video assignment is due before the exam, and then also we'll have the project proposal. So there are a lot of assignments. But then after March, there's just a 4th problem set, and then there's a project, and that's still a big thing, but it's just that one thing as the culmination for the course. But just keep your eyes on things as we are going forward, because after the break, there are going to be a few things right after one another. Question?
Individual, but the
yes.
project itself is a group project.
So I'm going to ask you to make individual proposals, and then I'll comment on those proposals, and you'll be able to choose your teams. But in some cases, if you tell me what your team is going to be, I might suggest, hey, I think these 3 proposals might fit together in a particular way. Or if you don't have a team set, then if there are kind of some really individual proposals, I might be able to suggest some alignment in terms of topics and interests. But I like to keep it individual before you get together. It doesn't mean you can't talk about your topics with others, or you can't, kind of guess who your team is going to be. But I do want the proposal to be individual, and basically I don't want you to propose the same thing as the other people that you would plan to work with. So maybe also is kind of lets us have a funneling process. If you have similar interests, you can propose 3 different things, and then through that process of reading and writing, can maybe come up with a better idea for a joint topic. And there'll be more details on that next week. Okay, so we'll have a quick recap of last time where we talked about electrostatics in solution and developed the basic representation for what's called the electrostatic double layer. So you recall that we discussed that in solution, most surfaces become charged, either by adsorption of ions from solution or dissociation of a part of the molecules on the surface. And if we take a case that we have a surface like so in solution with a negative surface charge, there is to enforce the requirement of electrical neutrality, you have a distribution in the concentrations of the ions away from the surface. And because you can't fit all the counter ions to neutralize the surface right on the surface, or it's not thermodynamically favorable to do that, you end up with a distribution in ion concentration. This means that the equivalent potential or voltage that is associated with the specific number of charges per area you have here gets neutralized over a distance. And this is the profile, the resulting profile of surface potential away from the wall. And where this action happens is what we refer to as the Dipole layer. And we were able to develop a simple model which says that the surface potential decays exponentially from the wall. And we can use that model to realize, for example, how the thickness of the layer decays when under constant surface potential, for example, as the concentration of ions in the solution increases. So in this example where when we increase the concentration of ions in solution, the thickness of the Dipole layer, or the rate of decay of the surface potential, decreases because you have more ions available to neutralize the potential. And you have a distribution of both the counter ions and the co-ions having lesser concentration near the surface because you have the counter ions trying to neutralize. And the total number of ions per unit volume is the same throughout, and when you get farther away, kind of like the analogy I tried to paint about being in the middle of the room, you don't see anything. It just looks like you see equal numbers of ions of both types moving around. And we went through this exercise to understand the reasons for electrostatics and the principle of developing the charge neutrality over a distance. And the application of this for us is to think about how nanostructures interact. And we closed discussing how we can superimpose the interaction potential from electrostatics with the interaction potential from, for example, van der Waals forces, and get an additive relation that lets us both qualitatively and quantitatively predict whether an arrangement of particles in solution, or generic objects, you could derive these for different shapes, is stable. And for example, when there's enough electrostatic repulsion to counteract the van der Waals interactions or create a sufficiently high energy barrier to forbid the situation from collapsing or coagulating, then you have a stable solution. And in a certain case, you could, for example, go from a stable solution to unstable solution by increasing that salt concentration, so you decrease the range, or the Dipole length governing the distance over which the surface potential and electrostatic interactions decay, and therefore essentially convert the net potential relationship from the case of A to the case of D below. And one of the last things I showed was this example, which comes from calculation of cases where we saw changing, for example, the size of gold particles in solution under otherwise the same conditions. A certain Hamaker constant, which is a term in the van der Waals equation, a certain concentration of salt, a fixed surface potential as a function, and plotting it as a function of separation changes the case of the curves here. And for example, what we're seeing here is that the effective barrier height, and the barrier height, because what's creating the barrier height is the repulsion, the electrostatic repulsion, is getting higher as the particle size increases. And then at the end, there was a question about why this peak isn't moving to the right. To me, it's moving to the right very slightly, but it's not moving to the right a lot as the size increases. And I think we can generally just look at this by seeing how the two terms in the equation scale. And I'm not sure exactly, I didn't get to check what model they're using here, whether they're saying the particles behave like planes or the particles behave like spheres. But if you looked at the scaling of the two terms of the van der Waals attraction term and the electrostatic repulsion term, which comes from the electrostatics, the derivation of the force, and then the integration of the force to get a potential, you could write out, for example, how this should scale. And in the case of treating them as spheres, according to the approximation where the radius is much larger than the separation, you would derive that the position of this peak doesn't change. But in this case, you can see clearly here that this sphere, the radius being 10 angstroms, is in fact smaller than the separation, so the curvature of the surfaces is very important. But I just wrote down the results for the case of spheres where the separation D is much less than the radius A, and This assumption is in the calculation of the electrostatic repulsion. And in this case, the repulsion due to electrostatic forces ends up being proportional to the radius times the exponential to minus the separation. In fact, it's minus the separation times the Debye thickness kappa, but the Debye layer thickness isn't changing with size, assuming we're in a planar case here. And then for spheres, the van der Waals just scales as r over the separation. So that says that if you, in the cases that we derived in class, if you change the radius, then the position of the maximum isn't going to change because they're both terms. You would be adding them are linear in the radius. But if you looked into the relationships for spheres with high curvature, there was a slide showing those last time, that may not exactly be the case. And to close the topic, I just have a few other short comments. One is we really didn't talk about how the surface potential is measured, or talk about another thing, which is the fact that in a real case, I said you can't pack all the counter ions up against the surface, but you do get some packing of ions against the surface. And therefore, you actually have a layer of counter ions that kind of sticks there, and then you start getting into the real double layer potential decay that we talked about. And this layer is called what's called the Stern layer, or the Stern plane, and then you have the diffuse layer where the potential decays smoothly as we derived. So in practice, what is typically called the surface potential is something that can be measured by doing experiments, for example, changing the pH of a solution and looking at the electrostatics of the solution, and that sometimes is what's called the zeta potential, and you can actually use this potential in the equation for the double layer to calculate how the potential decays. It's because these ions stick to the surface, it's actually really difficult to know what the real surface potential is. But in practice, if you think about things like slip and flow, if these ions are effectively stuck at the surface, the real interfacial action is actually not happening right at the surface, but at the edge of this layer where you may have some ions stuck against it. So in reality, what we may physically be talking about is the net surface potential resulting from the surface charge plus the ions that are physically there and not the ions that are moving around. And I think there is also an interesting overlap between electrostatics in solution and fluidics. In the case where, in our derivation, we said, well, we have a surface where it's just one surface, and we assume it's infinitely far away from everything, or it's many, many, many Debye layers far away from everything. And then when we talked about forces, we said, well, they have to be sufficiently close, but not, say, within a Debye layer separation to feel an electrostatic force with one another. But some even perhaps more interesting things happen, and there's some opportunity for devices and applications when you consider what happens when you bring two surfaces close enough together such that their Debye layers are interacting. This in principle happens if we have the two particles in solution and they're kind of feeling each other, but we didn't really say, well, what, other than stabilization, other than balancing those forces, what's an application of that? But, for example, if we consider that we might be able to construct a gap between two surfaces where the separation is smaller than the Debye layer thicknesses, then the Debye layers overlap. And you could say, well, maybe I'm going to make an additive approximation here where I'm going to add the potential from one surface and add the potential to the other surface and get a net curve. Well, what turns out is there's a saturation where you have a constant surface potential across the gap. And this is interesting, for example, for measurements of the dielectric properties of fluids. One application of this is doing impedance spectroscopy in small gaps. And another application of it is using ionics, or using electrostatic effects in solution to control the flow of fluids. And these pictures are from the last paper that I asked you to read last time, and also it's one of the video topics. And this is work done at Berkeley a few years ago, and what these researchers they did is they wanted to make a device analogous to a field effect transistor that uses a semiconductor and applies a voltage to change the charge density in it. They wanted to make an analogous device using fluidics. So what they have here, this diagram isn't really to relative scale, but they have, say, two fluidic reservoirs that contain fluid, and in fact they're microchannels that go here and here, and then they're connected by nanochannels. So they actually make silicon dioxide nanotubes by capturing them in a template. We'll learn about that in a couple weeks right after the break. And they're able to get them between these microchannels. And so flow can come in here and then go this way and come out there. And they have 3 electrodes in the device, just like a transistor. There's one on the left, there's one on the right, and then there's one on top. And by applying a voltage between this top gate electrode and the fluidic environment, they can alter the surface charge of the tube. So it's like a little nanochannel with diameter or with width that is in proximity to the Dipole layer thickness at the concentrations they're working at, and they can modulate the conductance or the flow of ions through the channel by changing the surface charge. Basically, if you have surface charge of one charge or another relative to the bias you're applying across the device, you can change how much pressure you might need to flow the ions across, because the ions, the charges on the surface and the ions that absorb on the surface are exerting forces in that environment. And there are a bunch of results in this paper, but one of the basic concepts that they demonstrate is that if you first, for example, consider a static case. If say if there's a static case where if you have ideally 0 surface potential, which really doesn't happen, then the liquid is going to flow. If it wants to wet the nanotube, it's going to flow in, and you're going to have an equal concentration of positive and negative ions. But if you have a surface potential either positive or negative, then just like in the case of one surface, we're going to have a higher concentration of the opposite ion on it. And they can manipulate the surface potential by changing this gate voltage. So you can see that if the gate voltage is positive, you end up with a positive surface potential, and then you end up with more negative ions in the channel to effectively neutralize that situation. Likewise, if the gate voltage is negative, then you end up with more positive ions in the channel, and that's what happens. And one measurement that can be done with this is at a particular bias voltage. I think this was 5 volts. You can see that they were able to measure the concentration of one of the ions as a function of the gate voltage they applied. And so what they had is they had their negatively charged ions in solution were a dye, so they were a charged molecule that was fluorescent. And by measuring the fluorescence intensity coming from this channel, which is an effective way to relate concentration, because the brightness of the light is like the concentration, they showed that as you make the gate voltage positive, you draw more negative ions into the channel, or you decrease the flow resistance to the flow of the negative ions, and the intensity increases. And based on the intensity and some calibration experiments they did, they were able to estimate the concentration of the ions in the solution. So this is one interesting example, and there are also other applications that are interest of using, for example, carbon nanotubes as fluidic transistors, or, for example, the effect of charge on flow through carbon nanotubes. One recent work from Livermore Lab is trying to use carbon nanotube membranes for desalination of water, taking advantage of the low flow rate through the nanotube, the high flow rate through the nanotubes, the high slip, to decrease the pressure drop across the membrane. And if they can combine that with this kind of electrostatic selection effect by, say, putting charge groups on the ends of the nanotubes that exclude the salt ions, then it may be possible to make a more efficient or lower energy consuming desalination membrane. Because if you can more flow through a membrane at the same pressure drop, you can decrease the energy consumption needed for that separation. But what turns out is that the concept of the Debye length is very important in that problem, because the practical salt concentrations for what's called brackish water, which is like lightly salty water you might find in a saltwater lake, from there all the way to seawater, is so high that the Debye length is very small, in fact less than a nanometer, and that means that something even such as a carbon nanotube is not really a nanofluidic, a device in the nanofluidic transistor regime. So it's in fact difficult, practically difficult, to do this kind of ion sorting from water that has practically relevant salt concentrations, even using channels of the carbon nanotube size. And that's something that is an interesting topic of research, and there are some startup companies working on it that are going on now. Okay, are there any questions about fluidics and electrostatics? All right, we'll move on to today's agenda, where we're going to talk about surface plasmon resonance. So totally different topic, talking about how light interacts with electric fields in small metal particles, and we'll talk about some applications of that in imaging and in sensing and lithography. And we'll at the end there, and we'll also talk about using very fast laser pulses to heat metals and some applications of that as well. And there's some reference there to his previous lecture on thermal properties. So the references we have today are two review papers that talk about surface plasmon resonance. The first one is more detail on the optical properties of metal nanoparticles, the introductory example we're building our understanding from. And then the second one is broader, talking about principles and applications of plasmonics and some more applications. And then the third paper is on the use of the fact that you can use this SPR effect, as we'll see today, to create very narrow optical fields smaller than the wavelength of light. So you can essentially beat the diffraction limit, and there's some interesting work on that with application to doing very fine lithography. And there are a couple of books that I'm not really considering these extra readings. We just wanted to let you know that if this is a topic you're interested in, we think that these two books are particularly useful for study of this topic. But everything we want you to know will be captured in what we discussed today and in the references that are posted. Okay, so Aaron's going to take over for a little while, and we're kind of going to go back and forth a couple times.
Okay, so like John said, the topic for today is plasmons. And if you've been reading the literature the last few years, you'll notice that plasmons are a really hot topic. This is the number of publications using the word surface plasmon in the abstract or the title. And you can see it's kind of like the new carbon nanotube, where the number of mentions just goes up exponentially. And it was discovered quite a while ago, but only recently, with the ability to make very small nanoparticles and nanostructures, have people been able to start to use these effects in devices, and that's why it's getting a lot of attention lately. So first question, what is a plasmon? And the word plasmon comes from plasma, which is like a gas of charged particles. And in the context of a plasmon, or a surface plasmon, we're talking about the electrons as the gas of charged particles responding to an electric field. So if you take a small metal particle where the field can penetrate most of the way into the particle, so it has to be maybe 20 nanometers, 30 nanometers, that's kind of the depth that the field will go into the metal, then the electrons will respond to the field and kind of slosh back and forth inside the particle. And depending on how long it takes for the electron to travel from one side of the particle to the other, that might be in resonance with the applied field. And when that happens, you get a resonance. We call it a surface plasmon resonance. And that charge density wave moves back and forth and will cause very strong absorption or scattering at particular frequencies. And it depends a lot on the shape of the particle. You can see from the geometry how long it would take the electron to travel back and forth. Or if there's a unique shape, like a rod or a square, there might be different resonances at different frequencies. And in addition, if particles are close together, there might be coupling. So all these things affect the resonances and make it very sensitive to small changes in the environment. And so the whole field of plasmonics is really exploiting these small changes to detect certain things about either the shape of the particle or what's around it in response to a field. So just a quick introduction of what it looks like to visualize surface plasmon resonance. This figure on the left, these small black dots are nanoparticles of gold, and impinging from the left is laser light at 800 nanometers. And you can see in the far field, there's this electric field, and then in the region immediately between the nanoparticles, it gets very bright and very intense. And that's a near-field surface resonance effect. So this field at 800 nanometers is exciting the resonance of these nanoparticles and causing this very strong local field. And on the right, here's a very old example of surface plasmons. This is a stained glass window, and this has been around for hundreds of years. What people would do is they would take metal salts, like gold and silver, and mix them with molten glass. And then once they're in the glass, the metal particles would coagulate into small nanoparticles. And when you get the right size and the right mixture, then there'll be resonances at certain colors. So for example, gold will produce bright red glass, or silver will make yellow glass. And depending on the angle that the light hits it, you'll see these fantastic colors. So even though people didn't understand really what was happening, they've been using this effect for a long time. So just really general picture of what is absorption, what is scattering. You can think of these processes for a general particle, where you have a field coming in, as there's an incident field, electric and magnetic field, and when they interact with a particle, the atoms inside the particle and the electrons will oscillate in response to it, and they will in turn re-radiate a field that will combine with the incident field and produce what we call the scattered field. And in addition, there's also some of that energy gets turned into heat or other forms of energy. So we have any energy that's re-radiated we call scattered light, and then energy that's converted is absorbed. And the way people represent this process is something called a cross-section, is a common term. You'll see different scattering cross-sections. So for example, for scattering, we define it as the power that's scattered divided by the intensity of the incoming radiation. And this has units of area. Likewise, you can define a scattering cross-section or absorption cross-section that will define the amount of power that's absorbed versus the incoming intensity. And the total amount of energy is the scattering plus absorption is called the extinction. And you can define an extinction cross-section, which is just the sum of the other two. So in general, you have all these processes going on. You have scattering and absorption. And sometimes you're interested in both, sometimes just one. Actually, if we go back for a minute, in this case, depending on if the light is coming straight through the glass and hits your eye, you might only see the effects of absorption. Whereas if the light came in at a glancing angle and scattered into all directions, then you would see certain colors due to scattering. So depending on where you stand, some of the colors might change in this glass window. Okay. So in general, when you have a particle or a collection of particles, the solution is pretty complex. And basically, it involves solving Maxwell's equations for a particular geometry and a particular incoming field. And there have been a few exact solutions worked out. The most common one is called me theory for a sphere in an infinite medium. And I'll just kind of run through the solution, but we won't go through it in any detail. The idea is that you'd start with Maxwell's equations, and you'd write them down for the particle, and inside you have a dielectric constants, so the permittivity and the susceptibility, that's epsilon and mu, and then you have those properties outside the sphere. And if you take Maxwell's equations and there it is. If you take Maxwell's equations and you take the curl of these bottom two terms, and then you apply a vector identity, you get these two wave equations for the electric and the magnetic field. So this is a vector wave equation. It has answer in all directions. And you can apply boundary conditions at the sphere surface where you require that the tangential components be 0. And I won't talk about the solution. It's just a bunch of math. But basically, you can go through and solve this exactly, and you can get expressions for the scattering and the absorption cross-sections. And those take this form, where you have the wave vector, and then it's an infinite sum of these terms where they're given by this collection of functions. And the psi and the zeta are called Bessel functions that you get from expanding these infinite series. And the important thing to notice here is the solution depends on this parameter m, which relates the dielectric properties of the particle and the medium, and also the size of the particle. And if you take just the first term of the sum, so if you truncate it, then you get what's called the Rayleigh limit, which is for a very small particle compared to the wavelength. And that takes a much simpler form shown here. And the form of this solution, you can see, depends on the radius. So for absorption or extinction, depends on the radius cubed, and the scattering depends on the radius to the 6th power. And likewise, there's the k is the wave vector, so it depends on the wave vector for absorption and the wave vector to the 4th power for scattering. So as you get much smaller particles, it will scatter with the 4th power. So that's kind of the takeaway point. And then you can see that even for a sphere, it's very complicated. So you can imagine for a rod or an arbitrary shape, it would be even more complicated. But in principle, there's nothing new going on. Yeah?
These are for the cross-section of the sphere.
Right.
Right? And then did they some cross? Or does that make sense to try to take a derivation across the whole, integrate across the whole sphere?
This is it's kind of an effective cross-section. So it's what it, if you were to represent it as a cross-section, this is the number you would get. Does that make sense?
Thanks.
Okay. Yeah. Let's see. So let me just show you a couple of plots of the solution. This is for absorption, scattering, and extinction for 2 different particles. The one on the left has a radius of 10 nanometers, and the one on the right is 30 nanometers. I think in this case it's gold. And the index of refraction around the gold particle is 1.5. So you can see that there's a strong peak around 550 nanometers. And for the small particle, there's almost no scattering. That's because it's got that strong dependence on size. And the absorption and the extinction then are basically the same. And now if you have a larger particle, in this case 30 nanometers, then the contributions from scattering and absorption are different. And you can see that the total extinction is just the sum of the two. So if you're measuring just one or the other in a measurement, for example, you would get different answers. And changing the size will change that parameter. Likewise, we can take that same solution and just vary the size of the particle. That's done on the left. So this is the effective cross-section again for absorption. And we can see that as we increase the size of the particle, the extinction goes up, although the peak doesn't move very much at all. So we're just increasing the efficiency with which it will absorb and scatter light. Likewise, if we change the environment around it, so we add some particles or some different medium to the solution around the particle, that will also shift both the amount that it absorbs, and also you can see it starts to shift the peak to longer wavelengths. So you can see how by changing the environment, you can get a peak that you can measure. And that peak is something that you could quantify and use as a sensor of some kind. So as you add, say, a certain chemical surrounding your particle, your peak would shift, and you could somehow relate that back to something you're looking for. And just another comment, for the solution for this sphere, we talked about how you get this big complicated series of terms, and we can truncate it and just look at the first term. And the first term is called like a dipole resonance. It basically has the same solution as a positive and a negative charge separated in space by some distance. And you can see these poles in the solution. When the particle gets bigger, it can support these higher order modes, say like 4 poles or 8 poles and so on. And in larger particles, you actually do see some of these resonances. So this is the quadrupole mode where you have these different lobes here. And if you look at the solution for the full solution, you'll actually see different resonances at different points. So there's this higher order resonance and then the dipole resonance. And as you shrink the particle down, the higher order modes start to disappear, and you're left with only this one over here, the main dipole resonance. Okay, and we've talked about small particles, but you also can get this effect for planar surfaces if you have the right material. So if you have a metal and a dielectric and you send in some light, then you'll get this effect at the surface of the metal, where you have charges responding to the field in a resonant way. So you'll get this strong absorption peak at a certain frequency. And you can imagine by using a rough surface or giving some texture, you can see how that would modify that absorption. And this effect is used in something called surface-enhanced Raman spectroscopy, where you'll have a surface, then you'll add some molecule, and this resonant frequency will match one of the frequencies of your measurement and amplify that effect a lot. And again, you can imagine that the mathematics of how you would deal with this are pretty complicated. Yeah?
Geometry dependent thing. This is a material property if there's a certain resonance for a plane for a certain metal?
Yes, definitely. There's geometry, so this the size, and then you've got the dielectric constants of the particle and the surrounding. And I didn't talk about it yet. I will in a little bit, but we've assumed that you can use the properties of bulk materials when talking about, say, the nanoparticle or the surface. And that's generally true as long as the particle is bigger than a few nanometers. Then you're usually okay using bulk properties. And if you don't want to think about it at all, you can just go and look up these properties as a function of frequency for a bunch of common materials. Although there are some more detailed models to kind of give you insight about why there are certain resonances. For practical purposes, people use typically gold, silver, copper, metals with a lot of free electrons, because you need to have the free electrons to have this resonance. Okay, yeah, so kind of following along with that question, if we want to understand how the material actually causes this effect and how that shows up in the dielectric constant, we can take a really simple model. This is called the Drude model for free electrons, where you have the electrons floating around in the lattice and they have some mass, so each electron has a mass, and it has some damping. So the electrons will bounce around and collide off each other, and that will effectively limit the speed with which they can respond. And in Maxwell's equations, instead of the electric field, typically you'll see this quantity d, the dielectric displacement, which is related to the electric field, plus a constant, the polarizability per unit volume, which basically gives you like the dipole moment per unit volume. So essentially, as the particle moves around, you get a displacement and a force in that direction, or a field in that direction. So in the end, you look for a term that looks like this, where you have the electric field, and then there's this dielectric constant, the relative permittivity, we call it. So a really simple model for this would be just to write down the equation of motion for a single electron and to pretend that it doesn't see the other electrons. And this turns out to be a pretty decent approximation. So like I said, you have the mass term, you have a damping term, and you have the applied field. So this is the force, actually. So you have the charge and the field. And this damping term is related to the time it takes for an electron to bump into another electron. It's called the collision frequency. And it's just related like this to the relaxation time. And if we assume that we drive it with a periodic source, then the result will also have this periodic form, where it's some displacement that's also periodic at the same frequency as the driving field. And this term is going to be a complex number, so it'll have a phase and an amplitude in response to your driving field. And you've seen this kind of equation before, I'm sure, and the solution is just takes this form, where you have the electric charge, the mass of the electron, and then on the bottom you have the frequency and the damping. So we can take that solution for x, we put it into the polarizability, and we substitute the whole thing into the dielectric displacement. And the result will look like this. So this collection of terms here is going to give us the permittivity. And the quantity on the top, this omega sub p, is called the plasma frequency. So you'll see this tabulated for different metals. And it's given by this collection of terms: the number of electrons per unit volume, the electron charge squared, and the permittivity of vacuum, and the mass of the electron. So that plasma frequency kind of gives a scale for this resonance effect. And we can take that permittivity and we can separate it out into real and imaginary parts, just like this, just mathematically. And you can also take it and relate it to the index of refraction. So sometimes if you look up the optical properties, instead of finding the dielectric properties, you'll find the index of refraction tabulated. And it's easy to convert from one to the other. So if you want to ask how well does this kind of simple model work, you can see that for very low energy oscillations, it works pretty well. So you're driving the electrons with a low frequency, and they basically follow this simple model. And then this is data from gold. You can see that as you begin to approach higher energies, the model breaks down. And the reason is because there's more complicated interactions between the electrons and the lattice around it. So you can imagine as you take the electrons and you displace them, they're not completely free. Even if you have a lot of electrons, if you displace them far enough, you've left behind a lot of positive ion cores that will pull them back. And depending on the band structure and all these other things, it might be pretty complicated. So a very basic model that would start to, I'll come back to that, that would take that into account would be to add some kind of spring term. And this is called the Lorentz model, you'll see, where it looks exactly the same as the previous case, except now we've added this force term with the displacement, just some kind of generalized spring constant. And you can go through the same exercise, just deriving it as the equation of motion, and you find that the answer is similar, except now you have this natural frequency that's given by k over m, the square root of k over m. And if you look at then what happens for the parts of your dielectric function, you see a strong peak right around this natural frequency. That means you get very strong response and strong absorption at this natural frequency. So this isn't really that important to know the details of this or why this model breaks down and how to derive it. And to get more details, you'd even need some quantum mechanics. But it should give you just a picture of where the material constants come from and how they relate to what's really happening inside the material. And just one more thing, if you want to know kind of what's going on, the plasma frequency is a useful number to keep in mind. So that frequency will relate to the frequency of light that you're putting in, and you can see that if you know the plasma frequency, so for example for a bulk metal or for a planar surface or for a sphere, you can relate the plasma frequency to the resonant frequency in these simple models. So for example, for a bulk metal, it equals the plasma frequency. And then for the sphere, for example, it's related by the square root of 3, and so on. And so you see it even for more complicated geometries, the plasma frequency will show up. So if you look up the plasma frequency, you'll say, okay, at least I know the ballpark area of where the resonant frequencies will be. Okay. So now John's going to talk about some examples of this stuff.
Okay, so given this quick understanding of how the optical properties of metal nanoparticles change with size and environment, there are a number of interesting relations to, for example, fabrication of nanostructures and also characterization of properties. And one really important and aspect that is driving this field is that to take advantage of these effects in a controlled way, you not only need to make really small structures, but you need to make really small structures very precisely. And if you can do that, then you can take advantage of this effect as a sensor, and you can also use the very precise structures you make to understand more about how the effect scales with size, because it scales with size, and you can imagine another effect can be the roughness of the surface of your particle or its proximity to another particle, and so on. And so I'll talk about a number of examples that help relate to that and also lead to some additional insights to the process itself. And one process that we'll learn more about later when we talk about self-assembly is, for example, a means of using an array of spheres as a mask for essentially a lithography process. And this process shown here is what's called nanosphere lithography. And here you basically, by evaporation of a solution containing microspheres, so typically polystyrene spheres that are made by a chemical process, you can arrange layers of spheres that are hexagonally packed, so kind of like a layer of oranges on the table. We'll learn about the mechanism of this assembly later, but what this process does is it uses this array of microspheres as a mask for deposition of metal. And say if it's possible to purchase these microspheres in a bottle dispersed in water, they have charges on their surface, so they're stable. So the spheres are, say, a micron in diameter. And because the spheres are a micron, the spaces between the spheres where you can basically see down to the substrate are a lot smaller. So you can then assemble this layer, deposit metal, say by evaporation or sputtering, and then lift off the spheres, and you're left with an array of nanoparticles, or you could say small islands of metal film that are in the sub-micron size range. In this case, maybe it's about 125 nanometers here, so it's about 1/10 the diameter of the sphere. And there are a few things that are interesting about these structures. One, of course, they're in a size range where these plasmon resonances become important. Second, they don't have this ideal spherical shape. So we'll be able to gain insights from the theory Aaron discussed, but we'll also see that the shape is important. And third, they're in proximity to other particles. And in fact, the fact that they are close to another particle can affect the resonance spectrum, because, kind of like the double layer, you can have interactions between the fields from one object to the other. And the effect you observe, whether you look at one particle or two or a whole field of particles, can be different because you sort of see it as an effective medium. Another thing that can be done is there are ways that these groups, and there's one group, Richard Van Dyne's group at Northwestern, that invented this and has really taken it to the limits to understand the fabrication and plasmon resonance. They can deposit another layer of spheres on top, and then before they do the metal deposition, and then they end up with smaller dots that are smaller and more separated. And so, for example, by tuning the nanosphere lithography process by using spheres with different diameters, so that's the big D here, and also by changing the thickness of the metal that they deposit just based on the thin-film deposition system, and also by doing this single-layer lithography or double-layer lithography, basically getting spherical particles or triangular particles. They're not perfect spheres or triangles. They then experimentally observe that they can tune the position of the primary SPR peak. And they, for example, have characterized the topography of the substrate like basically around where each sphere was, where it would be, contacting another sphere, like here and here. In between those two contact points, there's a particle. And you can see for these different conditions, the size of the particle varies, and also the shape of the particle varies when you go from the single layer process to the double layer process. And right here, the lines represent where they took an AFM tip, an atomic force microscope, to scan the profile. And this is the technique they use to measure the height of the particle and the spacing of the particles. But you can see that what they did here is they tried a whole bunch of different conditions based on their expertise in this lithography process. And this paper talks about the scaling and talks about their ability to tune it over a wide range. But this is really kind of mastery of this technique. But even with their mastery, the limitations of using an AFM, for example, to scan over these particles, because of the effect of the tip shape on the image and the relation, like the fact that if the tip has a certain angle, it's hard to measure the exact edge profile of the particle, means that these estimates of very small gaps between particles are only an approximation. So it really is hard to get an idea of the real true shape of the particle at a fine level, but certainly this ability to tune is there. And you would see experimentally that the position of the peak would depend on the height of the particles, the width of the particles, and the spacing of the particles. Another thing that can be shown is that you get interesting effects and effectively field concentrations whether you have sharp particles or rounded particles. And it just relates to how the electric fields are moving inside the material and the fact that you get very high field concentrations at points. And so this is just a result of a computation from the same group where they used a model of a single particle that was triangular and effectively looked at if it's triangular or if they snip off the corners. And you can see that another means of tuning this spectrum is by changing the shape of the particle in this way. And they called that, this is in the case silver, and called that a nanoprism. Now, both in terms of the theory and in terms of experiment, this behavior will also depend on the environment. And effectively here, you're changing the dielectric constant of the material that's around your particle. So in the way Aaron described that these effects interact with the medium within a certain dimension, on a dimension that's, say, tens of nanometers, if you change what's around your surface plasmon resonant object, then you can get a shift in the effective spectrum of that object. And here are examples from the same group where they took their arrays of metal islands fabricated by the Nanosphere lithography process and repeated the same experiment where, for example, they did the same experiment in different atmospheres. And here they were immersing it in different solvents, so in this case acetone, cyclohexane, pyridine, and also doing it as a control in a gas atmosphere, and showed that the spectrum depends on what molecules are actually around the surface. And then another way that they were, say, able to more controllably study this effect of the thickness and the properties of the medium around the metal is by depositing a thin layer of silicon oxide on the surface of the particles. And here they can actually correlate the shift in the peak relative to its native position with the thickness of this oxide layer, going from 0 to 100 nanometers. And in fact showed they got a pretty significant shift as they added a dielectric to the surface. And I think this, for example, is just showing the different peaks that are obtained with different thicknesses of oxide on the surface. So we really don't need to do the math to understand exactly how this scales, but certainly the effect of the environment is important in governing the optical properties of this system. So you can consider the metal particle to be kind of like people call it a beacon, or a very sensitive sensor for what is around it and what it's on its surface, in addition to its shape. And another thing of interest, as we saw in the case of the Nanosphere lithography process, is that the position of the peak or the spectrum is also very sensitive to the spacing between objects, because the fields that are created in one particle can interact with the fields that are created with another particle. So, it's challenging or pushing the limits of fabrication to make, say, one of these metal structures with precision of, say, a few nanometers. And we'll learn, get more numerical bounds for size control later on. But, you could say it's challenging to control and know the size of this island with nanometer precision. It's even more challenging, say, to control and know the size of the size of a gap between one island and another island. But it's interesting, for example, to study how this spectrum might depend on the spacing between a pair of particles. So what these researchers did is they used the Nanosphere lithography process to create just one single pair of particles, or one single pair of triangular islands. And if you assemble spheres but you use a very low concentration, they won't form a uniform layer. They'll kind of form little islands. And what they did is they did it in that way, and they just looked for a place where they had only 4 spheres, and therefore they were able to create only one pair. And so you can see here, this is an AFM image of 2 gold islands on a surface, and these are kind of like the shadows of the spheres that were there. And then they took this substrate, which, it's a lot smaller than this, but ideally it's shown, and probably not this clean, to be 2 little triangles of gold up there under an AFM tip. And they had an apparatus using optics where they were able to make a very, very sensitive measurement of the spectrum, of the optical spectrum. And they were also able to take images at the same time. And believe it or not, what they did is they made this pair of particles, and then they used the AFM tip to take images, and they also used the AFM tip to push one of them around. So, it's probably tricky, and I don't know how many experiments they did and how many times, the particles stuck to the tip, but they were basically able to do it in one case, and they tried to build a map of how the spectrum changes as the spacing changes. And they compared, for example, the spectrum of one particle, which they made from just 3 spheres together, to the spectra of 2 particles, where you have, say, a spacing of 85 nanometers, just measured by the AFM image, 45, and then 5, 0, and then they actually were able to get a case where they think they're overlapping and they're touching, and you can see a big difference in the spectrum in that case. And I think here they're using the spectrum for an isolated particle as a reference, and you can see that in relation to the general effects we've talked about, the effects of dipole or quadrupole resonances and shape and spacing, the spectrum is very different based on how much space there is between these 2 particles. And then the intensity of the spectrum drops down quite a lot when the particles touch, indicating that this gap, this very small gap between 2 very sharp features, is a zone of very strong enhancement. And I just think it's an interesting, way that really is kind of pushing the limits of the particle fabrication and the ability to change their separation. But it shows that if you could, for example, change this distance in a very repeatable and controllable way, you might be able to make a very effective and useful device that could study what's going on in this gap and maybe optimize the enhancement you could get by, putting something else of interest in there. And the paper also did some computations, just basically starting with Maxwell's equations and doing a more involved calculation of the scattered intensity as a function of wavelength. And I think they did a couple of calculations, one where they assumed they had particles with straight walls, and another case where they had particles with tilted walls. And you can see here both the theoretically predicted effect of the shape and of the spacing. And as the spacing changes, they're calling it the antenna gap, saying this kind of acts like a little antenna or a beacon. The position of the resonance peak shifts, and in their theoretical case where they had these kind of trapezoidal particles, they saw the emergence of 2 peaks, which is a result of the different shape and the resonance that is supported in that shape. I don't think, if you look back at their experiments, they saw as much of a shift as they predict theoretically, but the shift itself was certainly there. And they don't know exactly, because of the limits of the AFM technique to measure the shapes, they don't know exactly what the shape of their particles is, but it shows that the same types of things they have experimentally would be predicted as general trends based on the theory. And it turns out there's also another study that tries to attack this problem in a bit of a different way, using electron beam lithography, which is able to basically pattern pairs of particles by modifying a polymer and then depositing the film in there. This group was able to create pairs of, you could say, metal discs with different separations. And here, instead of having one pair of particles and changing the separation, they analyzed the spectrum of different pairs of particles, each with different separations. And they were able to see that they get the same kind of effect, that there is a shift to the red, to the lower wavelength, as the particle size, or as a shift to the higher wavelength, as the gap between the particles gets smaller. And you can also look and calculate, for example, the shift as the gap gets smaller, and it agrees very well in comparison to their computation of what this behavior should be. And another topic that's being studied widely as well is, for example, what happens as you put a molecule inside this gap between pairs of particles. And in fact, the enhancement that can be obtained to an optical spectrum obtained from a molecule is extremely high. And so it's in fact possible with certain molecules and certain dyes to obtain significant gains in the amount of intensity you would get from optical characterization of these molecules. So this is an example of a dye called rhodamine 6G, which has a well-known Raman spectrum, basically relating to the vibrational modes of the bonds inside this molecule. And if these molecules are placed inside a gap, or in fact if you take the Raman spectrum of, say, a cluster of gold particles that have been coated with this molecule, it has in fact been shown that you can detect the resonance or the presence of exactly one molecule, or you can get enough signal from one molecule such that you can see its Raman spectrum. And we'll see a bit more about Raman spectroscopy when we talk about carbon nanotubes in a couple weeks. But the idea that you can get a very strong electric field inside a space between two metal nanostructures has been shown, is being shown to be extremely important for detecting small quantities of chemicals. And if we can actually map out this relationship between shape and size and spacing in a controllable way, and if we could reproducibly create these pairs of particles in a way that you could say change their spacing, we might have an entirely new tool for doing these kinds of measurements and maybe obtaining information from things like individual molecules, or say monitoring events where a molecule might come out from solution and stick down at a surface. And in fact, one very practically useful application is, like what I just described, using the surface plasmon resonance to do biosensing. And there are commercial instruments that you can buy now that just use the native properties of a metal film. So not necessarily nanoparticles, but just look at the fact that if you look at a thin gold film, you'll see the effect of this plasmon resonance due to the electrons at the surface. And because changing the dielectric environment around it changes the spectrum, you can see when a certain molecule of interest comes to the surface and sticks and changes your spectrum. And this is facilitated by, for example, taking a piece of gold or a slide with a gold film on it and modifying it so it has, say, biomolecular receptors to a certain antigen or a certain molecule that's of interest. And one of the biggest applications of this is detection of markers for prostate cancer, what's called prostate-specific antigen or PSA. It's well known, for example, that you can use a particular antibody and you can immobilize that on the surface, and then if you inject a solution containing a certain concentration of PSA, you can relate the shift in the plasmon resonance spectrum of the gold to the binding of the PSA molecule on the surface. This doesn't have anything to do specifically with the fact that it's a PSA molecule, but it's the fact that you've modified the surface to have these receptors that selectively grab the PSA, and the fact that that then relates in a change of the refractive index of the surface. And another modification upon that, or a modification that might increase the sensitivity, is to not only bring in the PSA, but, for example, have a step before that takes your solution with the PSA that you're interested in and attaches it to gold nanoparticles. And then you can bring in the nanoparticles with the PSA on them, and those will kind of further amplify the signal that you get by this interaction. And so then you imagine bringing one gold piece next to another, and then you can get perhaps a more sensitive sensor. And what is done practically is you might, for example, have a substrate with a thin metal film on it, and you can use a beam of light and bring that upon the back of your thin metal film. And then by getting this binding reaction to happen, you'll see a shift in the surface plasmon resonance spectrum of the film. And I think what's done, I don't know if this is correct, but you can use a prism, for example, and because a prism essentially spreads light out, you can turn a change in the spectrum into a change in the angle of light that's reflected upon a detector. So you can use a very simple detection scheme. You can just look at a change in angle on a detector and relate that qualitatively to a concentration or the amount of shift that's happening. And if you have say only a few molecules, then you might get less of a shift than if you have a lot of molecules that modify the dielectric constant a whole bunch. And that, effectively, how much of a shift you can measure determines the detection limit of your technique. And here is a plot of the results, and this is the change in the angle of light coming off the sensor as a function of the concentration of PSA in the solution. And they were able to show, really nicely that they can detect this change over a concentration that's from 300 femtomoles to 3 nanomoles. So this is a pretty wide range detection scheme. And there's, for example, a lot of literature that talks about the use of these techniques to detect biomolecules. And in fact, here they're comparing. This paper is solely on use of different sensors to detect prostate-specific antigen. And you can see, you're welcome to look at this as a reference. For example, how the sensitivities of different detection schemes compare. And you can see, for example, typical SPR instruments, commercial chips that use this kind of what's called a sandwich assay. So it has something resonant, and you attach this PSA to that, and you bring that in proximity to the surface, can detect concentrations on the sort of nanogram or per milliliter format, which is getting to be competitive with other techniques that have been used for a while as well. And for things like biosensing, other things of concern are, for example, how much sample volume you would need and how much time you need to do the instrument. Basically, how much time you need to collect a signal to get enough information. Okay, so another example that I think is pretty interesting is how this principle can be used, for example, to process materials, and can also be used to characterize the production of materials. Because if you have, for example, a solution in which you're making some nanoparticles along the lines of the process of, say, nucleation growth that we'll address later, and you're making structures that have these properties, you could use the principle of surface plasmon resonance, or this change in optical properties, to monitor your process. And so these are pictures from a paper from Chad Merkin's group at Northwestern about 10 years ago, and they worked on a synthesis of nanoparticles in solution, and they were looking at how to make silver nanoparticles in solution by taking a salt dispersed in a liquid and learning how to change the conditions, the temperature, and so on to produce particles of certain size. And this all happened completely by accident, unexpectedly, because they basically left their solution, which they hadn't done their process on yet, out in the lab in the fluorescent light over the weekend. And they observed that when they came back on Monday, this is a true story, it was a different color. And then they're like, well, what's going on? Because typically when we make our structures, we don't see a different color happening. And what it turned out is that the interaction between the fluorescent light and the silver ions and small clusters in solution caused growth of these triangular shaped prisms. And as the prisms grew, you observed this size dependence effect of the spectrum, and you saw peaks appear and disappear and the peak position change. And they were able to then go back and do the research and study, for example, under what wavelengths of light this happened. They took fluorescent bulbs and they put a filter on it at 700 nanometers, and they saw that the wavelength of light between 300 and 700 nanometers was actually what was at work here. And they were able to relate the spectral evolution to the shapes of the particles versus time. And it's not completely clear what's going on here, but certain energies and certain wavelengths of light are effectively reducing the silver, or causing a light-mediated reduction reaction in solution, which my interpretation is in combination with the fact that you have a higher concentration at the tips of these particles causes them to grow into these triangular prisms. And they found that when they had effectively exhausted all the silver from the solution, all the source material, then the size increase of the structure stopped. And so it was a pretty slow process. It took a few days. Like, as you can see, it kind of happened over a weekend, about 50 hours or so. But they can and then produce these structures. And they also published some follow-up work when they were studying this process in further detail, that if they continued the process, and I think if what they did is if they changed the wavelength of light, they were also able to mediate the assembly of their initial prisms into these larger structures. And you can see that having different prisms in proximity allowed them to assemble into these kind of platelets where you had 4 triangles together. And that was also well observed in an evolution in this spectrum from the initial peak where you had isolated triangles to the assembly into these larger triangles, where now you can draw an analogy between the dipole effect and the quadrupole effect, where you're having different modes supported in the structure. And this is also mediated by exposing the material to light. And this is and it ends up where you have a bimodal size distribution, where you have pieces that have 4 triangles and pieces that just have 1 triangle. And you can see that there is a distribution, but they have these 2 sizes in the solution in the end. And this is a TEM image just showing the individual prisms that they made, and also ways that, if the solution isn't stable or there are interactions between the faces, the ways they might stack up. Okay, I think there's one last example, and then Aaron has a few closing slides. And this is the emerging area of using these large field enhancements for possible means of lithography. And as you know, in typical photolithography, you have a mask, or you have a plate that has some openings in it or transparent areas in it, and you use, for example, ultraviolet light to expose a photosensitive polymer and to then create a pattern. And the idea advanced by this recent paper is that because we can get very strong local fields and basically focus light beneath its wavelength using this plasmonic effect, we could possibly use a substrate of nanostructures, say nanoparticles or a metal film with holes, to create very strong and small fields of light that could be used to do lithography. And so what this paper did is they took ultraviolet light and created what they're calling here as a flying head, but basically it's a hard drive mechanism with a rotating substrate with a small piece of material that has metallic rings and therefore focuses the plasmons to expose a photosensitive material and create a pattern. And you can see here it was spinning on a substrate, and they had the light coming from a laser that was being switched at high frequency so they could pulse it on and off, and by spinning the substrate and moving the head, they could create patterns. And their ability to create very fine patterns is solely based on the ability to focus light into very, very small spots. And so here are some pictures creating metal rings with this shape. They were able to, by computation, focus the light down to a very, very, very small area. And then they were able to use this apparatus to modify, this is a special oxide photoresist, basically one that will be exposed when it gets heated up. And in fact, under this tip, things got pretty hot, and they were able to pattern lines as small as 80 nanometers. And it's just a demonstration of the ability to focus fields using this effect and to maybe combine it with some engineering to create particular patterns. Incidentally, at the level of demonstration, it's possible to use advanced optical lithography as used in the semiconductor industry to achieve dimensions smaller than this, but this is a really interesting demonstration where this type of interaction, the interaction between the beam and a metal mask because of the near field, is what causes this patterning ability. And they made structures in grid patterns over relatively large areas, and were able to write dots by pulsing on and off and coordinating the motion. And then this is the finest line that they showed in their paper a couple years ago. All right, I think we only have 5 minutes. Do you want to finish up, or? Okay, go for it.
So just one more example, and this kind of relates to some of the stuff we talked about earlier with thermal transport and also some of the surface plasmon stuff. So the example I'm going to use is cooking tumors using gold nanoparticles and exciting them with an ultra-fast laser pulse. So ultra-fast usually means, say, less than a picosecond. And Because it's happening so fast, like we talked about before, you can't treat the material as a continuum. You have to consider the energy carriers separately. So you have the light come in, and then initially, the light interacts with the electrons. And this is the part where you would get the surface plasmon resonance effect. And that would happen basically on the time scale of the light pulse, so maybe 100 or 200 femtoseconds. Then the electrons interact with themselves, and then gradually they interact with the lattice and heat it up, and then that heat gets distributed to the surrounding medium. So really quickly, what people want to do is use gold nanorods and attach some kind of binding mechanism and then have them stick to a cell, for example, a cancer cell. And then you could send in this light that would go through your body tissue but be absorbed by the nanoparticle, and they would heat up and selectively destroy the cancer cell. And people like nanorods because as you change the aspect ratio when you fabricate them, you can effectively tune the resonance over a wide range. So for example, you'll have two different modes, a longitudinal one along the rod and then a transverse mode. And you can see that for a given rod, you'll have these two very distinct peaks, and the strong one is the one we're usually interested in, is the longitudinal mode. So you have the electrons sloshing around along the length of the rod. In this example, I'm going to talk about, we have the rod, and then we put some kind of surfactant molecule on the surface. So in this case, we have this molecule called CTAB that has a hydrophilic head and a hydrophobic tail. And in solution, they arrange themselves in these kind of bilayer structures. So the tails kind of line up and the heads point out, and they'll either form these structures by themselves, or if you put a particle in, they'll form one around the surface. The same thing that, say, cell membranes are made of, and that kind of thing. And what we want to do is see the effect of this membrane on the particle, both in terms of how does it affect the surface plasmon resonance, and how does it affect the way that heat gets transferred to the surroundings. So when we shine the laser light on, we see this kind of complicated dynamic effect, where initially you have the electrons responding to the light within the first picosecond, and then this oscillation. And that's due to the whole particle kind of getting hot and then rapidly expanding, and it shakes. And from this, you can figure out the elastic properties of the particle and the size. And then after that, there's this kind of long thermal diffusion as the heat gets from the gold out into the particle, and then from there out into the surroundings where it would affect the cell. And just really quickly, we can see this behavior as we start to increase the concentration of this surfactant molecule in solution. So we go from having no particles in solution, and you get this one kind of curve, so there's excitement and decay. And then as you start to increase the concentration of surfactant, the shape changes, and then above a certain concentration, in this case 100 millimolars, it stops changing again. So that indicates that you've kind of been assembling this bilayer, and then once you get this critical concentration, it's stable and it's not going to do anything else. And this curve, from the decay, you can figure out the thermal conductance of that layer, and you can also map that to a shift in the plasmon resonance peak. And if we plot those together, you see that they coincide really nicely. So the blue is the interface conductance. So it's very high initially when there's no molecule on the outside. And then as you form this bilayer, it interferes with the heat flow. And you see that the interface conductance drops down. And then here's where the bilayer forms. And then it's basically constant as you increase the concentration. And this corresponds in the red curve with the shift in the absorption peak from around 760 nanometers up to 770. So that's, again, because you're changing the local dielectric constant around it. So this just shows how, both using resonance and also the thermal part, you can really see what's going on at the molecular scale. So how the molecules are interacting and when a certain chemical change is taking place. So that's it. Any questions?